So for this project, we're trying to control the temperature, the ambient temperature of a small enclosure and measure the humidity. Yeah. The apparatus is here. We have the enclosure with an inside sensor that measures the temperature and humidity, and an outside sensor that to compare it to that measures the temperature and humidity. We have the Raspberry Pi that is reading those and controlling the two Arduino heaters. In the middle, we have a fan that is attached above the heater to promote a well-mixed system, and some insulation on the enclosure.
Here are some of the equations we used to develop the theoretical model for this system. We began with a basic energy balance and used a resistance term for the heat transfer that included convection on both the inside and outside of the container, as well as conduction through the walls of the container. We eventually developed this transient model here, and then simplified the model with a UA term and an alpha term to make it simpler to actually model with our code.
So with that theoretical model, we also wanted to get the results of a step test on the system. So we ran a doublet test here, and you can see both the FOPDT fitted curve and the measured temperature. So we then fit our curve there to get the FOPDT parameters in response to this step input. With that, we then use those parameters to then determine our PID tuning parameters, which you can see controlling the system here across a varying set point. Two things to notice about this are, number one, that our temperatures readings are only given in increments, in integer increments, and so we actually cannot detect anything less than a full degree temperature change, resulting in this kind of step pattern. And that also results here in us not being able to control to within a degree because we can't detect to within a degree. So it's just kind of a property of our sensors that we have to deal with. And then also we can see here that we get, so that even though we've rejected a lot of faulty data readings, we still have a bunch of them coming through here.
Then we wanted to control or optimize our controller using the first principles model as a simulation. And so using the original FOPDT model and then IMC tuning parameters, we were able to model what the controller would do given this step test. You can see here that there's a lot of derivative oscillations, and here as well, and that causes a lot of problems with the controller. There's some overshoot, and right here it doesn't even make it. It's almost there, but doesn't quite make it before the step changes. And so we use this in order to optimize the controller.
And here we can see the different iterations we went through while we were trying to optimize the PID parameters. So this is our initial run, and then this is the run that happened just after we took out the derivative term, so set the D term to 0. You could see that it drastically improved. It got rid of some overshoot and got much closer to the set point. These next three are where we varied the P and the I terms, both to try and tune the controller as well as for stability analysis. And in doing this, we found that our KC term really can be any positive term and doesn't appear to ever really be unstable just due to the limitations of the system. And then here we can see our final tuned parameters with a quick rise time, almost no overshoot.
And so here's the system being controlled with the actual final tuned parameters, and you can see that it's really controlling quite well, though of course the first principles model does not match the real system perfectly. And so basically we've created a fancy thermostat. A thermostat may even be a better solution in this case, yet for the group that we're developing this for, they likely will actually need these additional abilities.